Yep. Okay, so thank you very much for inviting me here, and thank you very much for organizing that session. It's really awesome to see so many friends together. Well, I'm going to speak about recent work. Actually, we just finished with Damião Araújo on the optimal boundary and global regularity for degenerate fully nonlinear elliptic equations. To introduce the problem, it's about quasi-linear elliptic equations with a source term. I've written here like sort of a general form of such equations, be it in divergence or in non-divergence form. So what do we have? We have divergence of a matrix times the gradient of a function, or the trace of a matrix times the Hessian of a function. And that matrix A is a diffusion matrix. If A is the identity, these operators here are the Laplacian, and this, the divergence form equation, you usually would get from physical laws. For instance, when you have a substance that diffuses in a media. And the non-divergence form equation you would usually get from problems coming from probability and random walk, stochastic processes control, where we have some sort of random movement. And that A, the diffusion matrix, it measures exactly how the media, the X dependence, is how the media influences the diffusion or the random walk, so the spatial inhomogeneities, and the possible dependence of the solution or its gradient tells you how the diffusion is, the rate of diffusion is influenced by the very quantity U or by the flow of U, right, the gradient. So a standard situation is the uniformly elliptic case when the diffusion, while varying in space or with respect to the values of U and its flow, is always strictly positive, which means that there's diffusion in all directions always. May vary, but the rate may vary, but it's always strictly positive. And the situation that I'm talking about here is a diffusion. It's another physically relevant situation, is when the diffusion degenerates when the flow becomes slower and slower. And so this would mean a situation where the A in these operators is a positive, but becomes zero when the gradient is the zero vector. Exactly there. So when no flow, also the diffusion somehow is impeded from happening. Well, the simplest case of such a situation, well, I hope you would agree with me, or maybe the most natural somehow, the first model that you would think of, is take just the power, right? Power of the size of the gradient. Okay, so given some gamma, take A of x, u, and v to be the identity matrix, diagonal matrix, multiplied by the identity multiplied by the size of the gradient to some power. And that power obviously is sort of degree of degeneracy. If gamma is zero, there's no degeneracy. We have the equation here. If gamma becomes larger, the thing is more and more degenerate. That is, the thing is smaller and smaller when the gradient is close to zero. Right? And so when we set E equal to that, the divergence form equation turns into that equation here, which everybody would recognize as the P Laplacian if we call P equal to gamma plus 2. And the non-divergence form equation would be that equation over here. And so this talk is about this equation. I mean, and its more general versions. Right? So, but I'm already, let me already mention that the results that I'm gonna present here are new even for that very particular equation here. Right? So, yeah, so this is our model to start with. Okay, so what we are going to look at is regularity for the Dirichlet problem. So Dirichlet problem here is, okay, given an equation in our form, we can take, of course, not of course, but we can take quite more general things than just a Laplacian. Say, given a sort of an Isaacs operator, for instance, take, for instance, our sort of an extremo Pucci operator, and take that multiplied by the gradient to some power, and this is our operator. And so given coefficients B, C, F, G, that here are some smooth domains, some boundary portion of the boundary of this domain, and the Dirichlet problem would be just this thing over here, right? You have the equation, you have U attains continuously some boundary value. In this, here we consider C viscosity solutions in the sense of Crandall-Wishian ions. All coefficients are continuous functions. We don't bother about regularity of the domain, say it's smooth enough, C2. And what we study is the optimal regularity at the boundary, at this gamma, and also globally in omega bar, of solutions to such a problem in Hölder spaces, right? Hölder spaces are the CK alpha spaces that we usually know. Okay, so right, so let's me immediately start by saying that what we're gonna realize immediately is that the case gamma equal to 0, which is the uniformly elliptic case, and gamma not equal to 0, gamma positive, the degenerate case, have regularity properties that are fundamentally different, essentially different. Why? Because, okay, take the standard Dirichlet problem for the Laplacian, 0 data. Then it is very classical that more regularity you assume on the source, more regularity you get on the solution. So if, say, f is continuous, then the solution is C1 alpha for each alpha smaller than 1. If f happens to be C alpha Hölder continuous, then you is already C2 alpha. If f is even more Hölder continuous, CK alpha, then you is CK plus 2 alpha. And in general, if f is C infinity, you is C infinity, right? So more regularity on f, more regularity on u. While if we now take the corresponding degenerate operator, just this one, okay, I've taken the simplest in a sense situation. I've taken a right-hand side, which is just a constant, so even an analytic function, and I'm taking a flat boundary with the Dirichlet boundary condition 0. Then none of these features is verified for this equation as long as gamma is not 0, gamma is positive. Why? Because we immediately see that there is a one-dimensional solution, just xn to some power, and that power is precisely this power over here. So one-dimensional solution, even signed, which is precisely C1 1 over 1 plus gamma smooth. So none of this is true, I mean, because we have C infinity data here, very smooth operator, but there is a solution which is no more than 1 C1 1 over plus gamma. Yeah, and the essence, what we establish is that actually this very simplest solution, this one-dimensional power, this one-dimensional positive power, the simplest solution, is actually the worst in terms of boundary and global regularity, which means that this solution has the worst regularity. Any other solution is at least as regular. So the simplest solution already is the worst, in a sense. All the others are bad. So all the others at least as much. So that's what the theorems that will come up will say. Okay, right. So let me review a little bit of the literature for regularity of such operators. I mean, I'm really going to restrict to regularity precisely for this kind of problem. The literature of regularity is so large, it's out of reach, out of scope to review it in general. But for that particular problem, there was a series of papers in the year 2000 by Birindelli and Demengel, essentially setting a basis of the theory, such as maximum and comparison principle, relation to a first eigenvalue, Liouville type results, show the regularity locally and globally. Later, W. Fermat, Quas, and Imbert established Bachelman, Alexander ABP type estimates for some, also Harnack inequalities. Now, for some time at that point, it was open whether solution of such equations are C1 alpha. And the breakthrough result of Imbert and Silvestri in 2013 says that yes, for some small alpha, there is local C1 alpha regularity. Local in the sense that in the interior of omega, solution, or you can say that solutions are C1 alpha loc for some small alpha. And this was extended by Benitani and Dumengel to a global C1 alpha regularity. So let me just pause for a moment here and say, at the moment, at the point where some C1 alpha regularity is established, even for a very small alpha, or even actually for alpha equal to 0, for what I'm going to say, I can simplify these sorts of operators because the terms which are first order and zero order terms, they are already controlled, right? There is a C1 bound. So I can, for instance, throw away these first and zero order terms into the f of x because they already are controlled. So essentially, I'm going to write from now on operators that are the form gradient to a power times some second order thing. Damião, Ricardo, and Teixeira a little bit later proved that actually it is possible to establish an optimal C1 alpha regularity for these equations, and I'm going to recall what this result says here. And this work with comparison deals with the question of optimal boundary C1 alpha regularity as well as global C1 beta regularity, and I'm going to now review these notions, what they mean, and we'll go and give the results in a while. Right. So yeah. So first, a few comments about boundary and global regularity. What does this mean? And also a few comments about results small alpha versus optimal alpha, right? I think José Miguel will be actually telling us about differences in proofs of such results in a while. But let me say that first, what do I mean by a global estimate? Global estimate just tells you that you see one alpha up to the boundary, which means the gradient can be defined as a continuous Hölder functions up to the boundary. And the C1 alpha norm is bounded by a constant. This can be made more explicit. I'll make it more explicit in a while, but in a constant which essentially depends on the data, operator on the right-hand side here, on the domain, and on the maximum of the function here, the infinity norm of the solution. Well, proving this already for some alpha, even small, is extremely fundamental because it ensures that bounded sets of solutions are C1 pre-compact. This is fundamental, for instance, in existent theory, apart from being, of course, extremely important in regularity per se. But it has very, very large implications in existent theory for equations of this sort and for much more general nonlinear equations, actually. It's very various nonlinearities, U, du, and so on. Of course, this is another topic. Now, what is a boundary regularity? A boundary regularity is the following thing. What I mean is that if I take a point on the boundary and I look at the supporting hyperplane of U of a solution at that point, right? So given the supporting hyperplane, the difference between the function and the supporting hyperplane around the point on the boundary is controlled by a given power of the distance, and that power is 1 plus alpha. Okay. So in the global regularity, actually, this thing over here, U being in C1 alpha, is equivalent through an analysis argument to saying that this thing here holds, but this time for each 2 points in omega bar, not just fixing one of them being on the boundary. right? So this is what I mean by boundary and global regularity. Boundary means this, and global means either this or this for any 2 points in omega bar, and these are equivalent, as can be shown. And now, okay, so what is the Dc inequality here? This inequality, as I already said, it measures how quickly the function may get away from its tangent plane. Well, obviously, in this means that the larger you get alpha, the better your control gets, right? And so this is this sort of inequalities. They're very important in geometric estimates, for instance, in free boundary control problems. So where you want to really have a control of the way you can separate from for instance, here it's tangent plane. And of course, big wish is to be able to say that explicit alpha, eh? Of course, just a small alpha result is usually some alpha that just exists, but an explicit alpha, and the better it is, the higher it is, the better is one's wish in such a situation, right? So, well, that's the question we are asking. If we know the regularity tangentially on the boundary, so if this alpha prime here, the C1 regularity of the data on the boundary is given, what is the best regularity? What is the best regularity on the boundary? Okay. Or in other words, what this question here is if we have a hypersurface on the side, on one side of which we have an equation, and if we know the tangential behavior of the solution along that hypersurface, what can we say about its transversal behavior along this across the hypersurface? Behavior here means this inequality, of course, this sort of inequality. So, given this inequality only in the tangential directions with respect to x, with some exponent alpha prime, what is the best exponent in the normal directions, right? And this also to gain some better understanding, it's good to compare that question about boundary regularity with the question of interior regularity. What is the interior regularity? So this will also permit me to recall the result of Araújo, Ricardo, and Teixeira. So interior regularity just tells you, okay, we have some domain, say above, and then in some interior point, in any interior point very far from the boundary, we have the same sort of separation of view from the tangent plane at the point. Here I've written 0 for now. And so what's the difference, and how does this compare such a result, such a problem compared to a problem of a boundary regularity? See, neither the interior nor boundary regularity contain each other as problems, because for the interior regularity, you have less information in the sense that you don't know a priori the behavior of view along some surface. Essentially, you don't know along some surface. This means give the behavior of view along n-1 directions. Wonder what's happening in the nth direction. So for interior result, you don't have such information. You're just asking what's happening around the point. But on the other hand, the equation itself is satisfied in the whole neighborhood of the point. So you have an equation in a neighborhood. While for a boundary regularity, you have information in n-1 directions, but the equation is not satisfied across that hypersurface. It's satisfied, you don't have a neighborhood in which you have the equation. So you just deal with an equation on one side, right? So these two problems are in a sense complementary. They are first of all complementary, but none of them is actually, neither is contained in the R. You're asking about different things. Okay, so the Araújo, Ricardo, Teixeira result gives an answer about the optimal regularity, or almost an answer. And it tells you, okay, so first of all, we necessarily will always be bounded. The optimal alpha will never go above 1/1 plus gamma, because we have these very standard solutions, at least, that have this behavior. And simply 1 over 1 plus gamma is the intrinsic scaling of such an equation. So this is really like a bound from above. And apart from that, what we need to assume and have to assume is that we do not go above the best exponent for which the estimate holds for the solution of the pure equation, just the uniform elliptic equation with constant coefficients, right? So to start with, if gamma is equal, if gamma is 0, this is a very celebrated result by Caffarelli from 1898. And so they extend it to gamma positive, in which case you have to add this into. Okay, this has the slight drawback that the Caffarelli's argument gives you here a strict inequality. It's not completely clear if you go on top of alpha f on one hand. But what's also annoying is that in general, there is not an explicit expression for alpha f, for general f. And that makes part of a big black forest in the theory of fully nonlinear equations related to optimal exponent in ABP inequality, Weak-Harnack inequality, reverse LP to LQ inequalities. So in general, there's not a explicit expression for this alpha f. But if particularly if the operator is convex or concave, for instance, the Laplacian obviously is both, then there's no restriction. You can take alpha to be 1. Oh, but on the other hand, we also know that thing here is the Evans-Krylov theorem. But on the other hand, there are examples of Nadirashvili and Vladut that tells you that, on the other hand, we can always find operators that, of course, would not be convex or concave, for which the corresponding alpha is as small as you want. And so, yeah, so there is this, the fact that this is the optimal. In any case, there's optimality up to this strict inequality here. And the fact that alpha f is not known in general is nobody's fault, or respectively everybody's fault. We really don't understand this. We are very far from walking into that at this point. Well, so that's the result in the interior regularity. Now, boundary regularity. So here I've written the problem and the boundary regularity. I've written it in a half wall to simplify. Say the domain has been smoothened. And what is the optimal alpha for a boundary regularity result? Here 0 is part of the boundary of the domain, right? The boundary is flat thing, and 0 is on the boundary, and the equation is given on one side of it, right? Well, what we show with the mu is that the optimal alpha is exactly what you cannot go above. First, obviously, you cannot go above the tangential regularity because it's part of this inequality. So you're always limited by alpha prime, and you're always limited by the intrinsic scaling. We know that there are solutions which have exactly this regularity. And this is optimal. I mean, all solutions are C1 alpha with this exponent here. As I was saying, right, this that very simple one-dimensional solution is the worst one. That's observe. This is exact and explicit, just in terms of this the boundary data and gamma. There's not an unknown constant. There's not an alpha f, which in general we do not know, and there's no strict inequality. There's equality here. It's really. It's explicit and exact. In a sense, it also shows that the interior regularity does not influence the boundary regularity as well. Right? So why is it so? Well, yeah, and then there's a way to put together boundary and interior regularity. That's actually a problem, but there is a way, and then you show that the optimal global regularity is the minimum between the optimal interior and the optimal boundary regularity. So this inequality here, I've written here the constant in a more precise way in terms of this data. So the optimal regularity is, okay, you take the optimal boundary, you take the minimum of that with the interior regularity. So where does where does this thing over here come? How does this thing over here come up? Let's see. So about the boundary regularity, but let me first discuss a little bit the uniformly elliptic case. This already has to be observed that there's the result for gamma equal to 0, the very uniformly elliptic equation with the question about exact boundary regularity. So gamma equal to 0. Recall that since for such equations we already have C1 alpha for very small alpha. Extremely general results in that direction, so due, for instance, to Gabi, earlier to Winter, Gabi Nome, who just spoke. So I'm writing here only second derivative because first and zero order terms can be considered as part of the x dependence. And then the fact is the following theorem holds. The boundary regularity is the same as the tangential regularity, right? So the normal regularity is the same as the tangential regularity. Okay. So for instance, it tells you that if you are given the behavior of a function along n-1 direction, in the remaining n directions, it does not behave worse. It cannot behave worse. So for instance, these examples of Nadirashvili and Vadut, they cannot be functions that that would behave badly only in one direction. It has to be more. They have to be, actually they are sort of homogeneous things, but it at least tells you that there's no way you will have n-1 directions in one way and worse in the nth, in particular, right? So here the same, right? Well, this result is where does it come from? It's we use it in the proof of the full theorem, and so we write a proof, even though actually there's been recently quite a number of works, related works, which establish optimal results for uniformly elliptic equations, even though I cannot quote these things, so we need to write it. But where does this come from already in the uniformly elliptic case? The point is that you can see this problem, you can study this regularity by a Caffarelli's perturbation method, of course, boundary adaptation of that method. You can do tangential analysis. Many of you know what this is actually very well. And the point is that this problem is tangential to that problem. I mean, just constant coefficients equations on a flat boundary with a zero boundary condition. And a result we proved with Silvestri in 2014 is that viscosity solutions of this thing over here are C2 at the boundary, right? They're C2 at the boundary, even C2 alpha. And so you can access from this C2 information any C1 plus alpha information for a problem which is tangential to that one. So that's essentially the reason for which this thing here holds. Maybe a few comments also on that theorem with Silvestre. Okay, I think I'm having less and less time now. Well, we actually, okay, how much time do I need? Yeah, maybe 5 minutes I'm gonna ask you. So in that, there are two types of problems studied in that paper. Solutions of the so-called S-star class, which are just two extremal inequalities, or solutions of equations. So a result that's been around for some time, which we proved probably with a clean proof, but it's been known, and it's due to Kryov for smooth solutions, and various forms of it had appeared earlier for weak solutions, is that solutions of this class are C1 alpha at the boundary. But then you may think normal derivative of a solution can be seen through difference quotients as a solution of this problem. It is really the core of the C1 alpha regularity theory. So you may gain one derivative when you have a solution of an equation. And we prove that, but it's actually not an easy proof when it's one of these situations where going from smooth to viscosity solutions requires some serious work. And so actually to this theorem, a tangential analysis can be done. Already with Silvestre, we did some tangential analysis, which was suboptimal because we were aiming it as C2 alpha results in a whole neighborhood of the boundary, which is a different sort of problem. Recently, there's been a result where optimal tangential analysis, in particular to that one, has been done. A very, very general and exact and a complete result by Braga, Gomez, Moreira, and Wang appeared to us here. It's really very, very complete, which essentially tells you that a very huge class of solutions, solutions of a huge class of inequalities are tangential to this result. And so the C1 alpha with optimal alpha. And recently there's been further preprints by Liang Wanzan and also the Silva and Gabi, João Vitor and Gabi. Okay, so actually the point is that you can do tangentiality to this in the uniform elliptic case. Now, on the other hand, interior regularity for the P-Laplacian equation, you remember that divergence form equation I had in the beginning, the P-Laplace equation, was obtained by Damião, Eduardo, and José Miguel a few years ago. That's an exact result too, and it tells you if P harmonic functions are C1 alpha for some alpha which is bigger than this scaling exponent, then the solutions of this equation are exactly in the optimal space. They are exactly where you want them to be. Now, the proof of that result is delicate and very nice. It does tangentiality, but it's a sort of a two-track tangentiality argument. So when you do a Caffarelli type of iteration, at each step of the iteration, you may see the thing like that. At each step of the iteration, you look how small or large the value of the gradient is with respect to the corresponding scale where you are. And then you can do it where you can say if it is small at the scale, you can get information from the tangential problem, which here is the P-Laplace equation. And this permits you to move one step further, thanks to this thing over here. And if the gradient is large, you can actually rescale in terms of the value of this gradient and get an equation where now this rescaled equation, where now this gradient will appear as something bounded. So you get just a uniformly elliptic equation. Okay, so combining these, you get this thing at the end. It's very nice. It's essential that you have C1 alpha estimates for this equation for small alpha because you need compactness for that equation. And so once more here, our result. And its proof is a sort of a two-track tangentiality, but with boundary control. So either we are tangential to a uniformly elliptic equation, and then we can use the result I had with Silvestre that says there's a C2 boundary regularity, or we rescale to a uniformly elliptic equation for which the result is already proved, as I said. Okay, and also we need the C1 alpha estimates. Interesting additional difficulty appears when you join the interior and boundary estimates into a global one. This joining is not absolutely, it's not just analysis. You need to reuse the equation. You make some operations, which in particular infer removing a linear function from the equation from U, and that's not very nice with respect to this equation. So there's a little difficulty. I mean, there's some difficulty there, and you have to be careful with the values of the gradient also. But well, that's all I had to say, and thank you for being with us.